Section 10.5 discusses linear systems that have repeated eigenvalues. In section 10.4, we looked at linear systems with distinct eigenvalues and distinct eigenvectors and two distinct solutions. So now we have to examine what happens when we get the same eigenvalue twice. So let's look at this particular example where we have no forcing function. So we have a homogeneous system. And we have our coefficient matrix A, which is made up of 0, 1, negative 4, 4 times y. So when we do our A minus lambda I to find our eigenvalues, we find out that our characteristic equation is lambda minus 2 quantity squared equals 0, which means then that lambda 1 is 2 and lambda 2 is also 2. But if we use lambda 1 equal to 2 and we find our eigenvector, we find that we get the vector 1, 2. So our first solution would be y1, which is the vector 1, 2, times e to the 2t. So since the root is repeated, we may be tempted to try that method that we learned back in chapter 5 when we had repeated roots, which was to multiply by a t, and then do t e to the 2t. So we might be tempted to try that. And if we substitute y back into our problem, however, we find that the only solution here is trivial. We get C1 equaling C2, which is 0. So another thing that we could try is to try to find a second solution of the form where we have a function of t and both entries of our vector, right? Both elements of our vector times e to the 2t. Where we're basically using a variation of parameters technique like we learned in chapter 5 and plugging y2 into our original differential equation or system gives us the following result. Now remember, because our vector is made up of functions of t and it's also multiplied by a function of t, we have to use the product rule. So this is a big product rule for y prime. Right? A big product rule for y prime. And so that would be our vector times the derivative of e to the 2t, which is what we see in the first term. And then we have the derivative of our vector times e to the 2t in the second term, and we find their sum. So this is our y prime equaling a times y, right, where this is a and this is y. If we subtracted the vector of c1 of t and c2 of t times 2e to the t over to the right-hand side, and we combine some like terms, we find out that we can get back to a linear system of the form c1 prime is equal to 2c1 plus 1c2, and c2 prime is equal to negative 4c1 plus 2c2, which we have here in the form of c1 prime equaling these coefficients times these variables, right? Which are really functions. So negative 2c1 plus 1c2. c2 prime would be negative 4c1 plus 2c2. And you can see that down here, where I wrote it all out. From this, we can see that c prime 2 of t is equal to 2 times c prime 1. So you take c prime 1 and multiply the whole thing by 2, you're going to get this exact expression. By integrating, we can obtain then that c2 of t is equal to 2 c1 of t plus some arbitrary constant a. By substitution, we can also find that c1 prime of t is a, or c1 of t then is at plus b. We can use this information then to obtain a set of solutions for c1 of t and c2 of t. That system then is written as c1 of t is the at plus b, And C2 of t is 2at plus 2b plus a. And so we can now rewrite y2 as the vector 1, 2 times at, and then e to the 2t, plus 1, 2 times b e to the 2t, plus 0, 1, a e to the 2t. For those of you unfamiliar with linear algebra and wondering where this came from, we are looking at our coefficients here. And remember, we're looking at a y2 of the form c1 of t, c2 of t, times e to the 2t, which is where this e to the 2t came from. So that's where all of this is from. What we said is here, take the coefficients of the at, which would be 1 and 2, and then the coefficients of the b, which are just 1 and 2, and then coefficients of a, which are 0 and 1. And that's where each of those vectors came from. And since the vector 1, 2 times b e to the 2t is the same as y1, we let b go to 0. So this is the same as y1, so we're just going to let this guy go to 0. Just going to let b 0. And then if we let a equal 1, then what we end up boiling down to here is a 1, 2, right? 1, 2, t e to the 2t plus a 0, 1 e to the 2t. And that's what we have here on this next page. We can see that our second solution then is the vector 1, 2 times t e to the 2t plus the vector 0, 1 e to the 2t. So our general solution is c1 y1 plus c2 y2 plus c3 y3, etc., right? So here we have a c1 y1 plus a c2 y2. So we're looking for y being c1 y1 plus c2 y2. And so we end up with c1 e to the 2t times 1, 2 plus c2, and then we have that entire solution from up here. But there has to be a better way, right? This seems a little complicated considering the number of problems we're going to have to do with these. So instead of going through this whole process every time we want to solve our system of linear ordinary differential equations with repeated eigenvalues, we have a theorem from our textbook that will offer us a more direct method. It says, suppose the n by n matrix A has eigenvalue lambda 1 of multiplicity of at least 2, and the associated eigenspace has dimension 1. That means that all lambda 1 eigenvectors of A are scalar multiples of an eigenvector. And I put it in the same notation we've been using. Then there are infinitely many vectors u such that A minus lambda 1 I times u is equal to our eigenvector. And moreover, if u is any such vector, then y1 is equal to our eigenvector e to the lambda 1 t, and y2 is u times e to the lambda 1 t plus our eigenvector times t e to the lambda 1 t. And they are linearly independent solutions of our homogeneous system. And so this probably sounds a little more complicated, but it gets a little bit easier once we start looking at example problems. We're going to have two different example problems to look at, and hopefully that will make you feel more confident in solving linear systems of ordinary differential equations that have repeated eigenvalues. For example 1, we want to find the general solution of the system y prime is equal to the matrix 11, negative 25, 4, negative 9 times the vector y. So just like before, our first step is to find our eigenvalues. So let's do that first. So we look at our determinant of 11 minus lambda, negative 25, and 4 and negative 9 minus lambda. We end up with our characteristic characteristic equation of 11 minus lambda times negative 9 minus lambda minus 4 times negative 25. We want this whole thing to equal 0. So we have a negative 99 plus 9 lambda minus 11 lambda plus 100. So we really, oops, and we forgot a lambda squared. Let me put that back in here. There we go, and then plus our 100. And so we end up with lambda squared, and then 9 minus 11 gives us a negative 2 lambda. 100 minus 99 gives us plus 1. So here we have lambda minus 1 times lambda minus 1. So we do get that repeated eigenvalue of lambda 1 and lambda 2 both being 1. So let's find the associated eigenvector for our particular eigenvalue. So step 2, let's find our eigenvector. Okay, so we're looking at lambda 1 equaling 1. So we would end up with A being 11 minus 1 and negative 25, 4 and negative 9 minus 1. And we're going to augment that and have it equaling 0. So if we just simplify that, we have 10, negative 25, 0. We have 4, negative 10, and 0. So now we have to simplify things a little bit. So let's start with dividing the first row by 5. So let's just do 1/5 R1, and let's do 1/2 R2 and see what we come up with. We end up with 1/5 makes this 2, negative 5, and 0. And 4 divided by 2 is 2, negative 10 is negative 5, and 0. So now all we really have to do is say negative R1 plus R2 is our new R2, and we end up with 2, negative 5, 0, 0, 0, 0. So 2x1 minus 5x2 equals 0. So 2x1 is equal to 5x2, which tells us that our eigenvector would then be, well, let's see here. If we let x1 be 5, then x2 is 2. And that would make them equal. Right? So we end up with an eigenvector that is 5 and 2. So our first solution y1 then is 5, 2, e to the 1t. All right. So we've done the heavy lifting essentially. Now we have to find out what y2 is equal to. So let's scroll up here a little bit and see if we can use that theorem to help us out. So step 3 is to find y2. All right, so what we know is that we can find y2 using that theorem that we just looked at that said it is u e to the lambda 1t plus our eigenvector, right, times t e to our eigenvalue times t, right? And remember, then this is where a minus lambda 1 I, right, times u is equal to our eigenvector. So what does this look like? Well, this is where things get a little bit different than what we've done before. So what we're going to do is we're going to take our reduced coefficient matrix, so A minus lambda I, which is the 10, negative 25, 4, negative 10 that we found before, and we're going to multiply it by u, which is going to be u1, u2. So we're doing this part and this part. And it has to be equal to our eigenvector, which is 5, 2. So very much the same way that we've been solving for our coefficients for our general equation when we have initial conditions, and much like we've been solving for our eigenvectors, we can do the same thing now with an augmented matrix to help us solve for u1 and u2. So if we write this out as an augmented matrix, we have 10, negative 25, 4, and negative 10, but now instead of it being equal to 0, we want it to equal our 5, 2 vector. And here's the best part, because we already wrote down the steps that we needed to use to reduce this to solve for our eigenvector, we can use the same steps to help us reduce this augmented matrix. So let's start with what we did before, which was 1/5 row 1 and 1/2 row 2. So we end up with 10 divided by 5 is 2, negative 25 divided by 5 is negative 5. Now here's where things are a little different. 5 divided by 5 is 1. And in our second row, we divide everything by 2, and now we have 2. We have negative 5, and we have 1. And so the best part is it's exactly the same as before, where we end up with a second row being a multiple of the first row. So we can just say then negative R1 plus R2, just like we did before, is our new augmented matrix, which is going to look like 2, negative 5, 1, 0, 0, 0. So what this tells us then is that 2u1 minus 5u2 is equal to 1. So let's solve for u1 in terms of u2. So 2u1 is equal to 1 plus 5u2. If we continue to solve for u1, we find out u1 then is 1/2 plus 5/2 u2. So that means our u vector is u1 and u2. So u1 is 1/2 plus 5/2 u2, and u2 is just u2. Now here's where things get really fun and really different than what we've done before, because we have to do something different yet again. We're going to say, now let u2 be 0. Much like we were picking values when we were finding our eigenvectors, we're going to find the same thing here to find our u vector. So if we let u2 be 0, then we have u being 1/2 and 0. And now we've found our u vector, which means that u times e to the lambda I t plus our eigenvector times t e to the lambda 1t is where we're going to find our general solution. So if we write it down here at the bottom, our general solution, so suppose this is step 4, our general solution is going to look like y is equal to c1 y1, which is 5, 2, the vector, times e to the t, plus c2 and y2. Well, this is y2. U e to the lambda 1t plus our eigenvector times t e to the lambda 1t. So c2 times u, which is 1/2 0, right? E to the lambda t, which lambda is 1 here, so e to the t, plus our eigenvector 5, 2, times t e to the lambda t, which is again 1, so just t e to the t. So we end up with our final general solution looking like C1 times the vector 5, 2 times e to the t plus C2, and then times the entire expression for Y2, which is the vector 1/2, 0 times e to the t plus our eigenvector 5, 2 times t e to the t. And that is our final general solution. We're going to try one more. Let's try another example. And I'd like for you to pause and try to find the eigenvalue first, which is going to be repeated on this one, and see if you can come up with your eigenvalue and your eigenvector before we move on to finding our vector u that helps us to find y2. All right, let's try it together and see if we got the same answers. So we find our eigenvalues, then we're looking at the determinant of 7 minus lambda, -4, 1, and 3 minus lambda. So we get 7 minus lambda times 3 minus lambda, minus -4 times 1 for our characteristic equation, and we want it to be equal to 0. So 7 times 3, 21. Let's see here. So -7x and -3x. Oh, sorry, not x, lambda. 7 lambda and -3 lambda. Let's see here. And then plus lambda squared. And then plus 4. So we really get lambda squared minus 10 lambda. And then 21 plus 4 is 25. So that looks like lambda minus 5 times lambda minus 5 to me. So we get our lambda 1 is 5. So now let's find our eigenvector. And we only have one this time because we only have one distinct root. So we only have one eigenvector to find. And then remember, we'll use the same theorem as the last problem to find y2. So if we find our eigenvector for lambda equals 5 for lambda 1, we end up with, let's see here, 7 minus 5 and -4, 1 and 3 minus 5, augmented with a 0, right? A 0 vector. So let's just simplify it a little bit. 7 minus 5 is 2, so we get 2, 1, 0. -4, 3 minus 5 is -2, and 0. If we said 2 row 1 plus row 2, we're going to find out then that we will get 2, 1, 0, 0, 0, 0. So we have 2x1 plus x2 equals 0, or x2 is equal to -2x1, right? So if we do that, then we have an eigenvector here of, if we let x1 be 2, then x2 is -2. So we get an eigenvector of 1, -2. So how does this help us find our u? Well, we have a pretty easy going eigenvector and eigenvalue process, so let's keep it going. So for step 3, we want to find y2. And remember, y2 is of the form u e to the lambda t plus our eigenvector times t e to the lambda t, right? So, and then again, this is where a minus lambda 1I, right, times u is equal to our eigenvector. So a minus lambda I is going to give us our a vector minus 5 on the diagonals, right? So we're going to find 7 minus 5 and -4, and then 1 and 3 minus 5. And it's all times u1, u2, and it's going to equal our eigenvector, which is 1, -2. So if we write this as an augmented matrix, our life will be a lot simpler. Let's scroll it up a little. And we're going to write it as 7 minus 5 is 2. A -4 here. 1, 3 minus 5 is -2. And then we have 1 and -2. So again, we can follow the same steps we did above, which is 2r1 plus r2. And let's see what we get. 2 times 2 is 4. Right here, we keep our 2, 1, 1 in the first row. 2 times 2 is 4. 4 plus -4 is 0. 2 times 1 is 2. 2 plus -2 is 0. 2 times 1 is 2. 2 plus -2 is 0. So in fact, we get 2u1 plus u2 equals 1. Right? So we can say u2 then is equal to 1 minus 2u1. And that means that u is u1 and 1 minus 2u1. And this is where we step in and do the same thing as last time. We're going to say let u1 equal 0. Then we have u being the vector 0, 1. Because we let u1 be 0, and u2 depended on u1. So when we eliminated the u1 term, we're left with just 1. So we get a vector u1. So that means that, I forgot to write in y1 up here. So y1 was the vector 1, -2, e to the 5t. And that means y2 is going to be this u, which is 0, 1, times e to the 5t, plus our eigenvector 1, -2, times t e to the 5t. And now we just need our general solution, which puts it all together. So step 4 is our general solution, okay, which tells us that y is equal to c1y1 plus c2y2. So y here is c1, 1, -2, e to the 5t, plus c2, and now in parentheses, this whole solution, which is 0, 1, e to the 5t, plus 1, -2, t e to the 5t. And that is our general solution to this system that has a repeated real root to the characteristic equation, which means it has a single repeated real eigenvalue. So I have a few homework problems listed after this. Just make sure that you check the posted assignment for the written homework to see which of these two problems are assigned for this section.